So Cliff, we're very excited to have Cliff here. And I can tell you a little bit about him because I happen to have it all written down right here. But Cliff received his BS in physics from Cornell University in 1974. And he worked on Earth and Martian atmospheric modeling with Carl Sagan. And after receiving his PhD in atmospheric sciences in 1978 from the University of Washington, he was an assistant professor at the University of Maryland from 1978 to 1981. He then moved on to the University of Washington, where he's currently a professor of atmospheric sciences. And his specialties are weather prediction, numerical modeling, the influence of topography on weather systems, the structure and evolution of weather systems, and the weather of the western U.S. He's currently the lead scientist for the Northwest Modeling Consortium, a group of local, state, and federal agencies building a cutting-edge weather prediction capacity for our region. No. Professor Mass is also involved in public outreach activities, which is probably why you're all here. He's a commentator on a weekly weather segment on radio station KUOW, and he produces an informative and popular blog. He's written over 85 refereed papers, has served as an editor for several professional journals, and is a fellow of the American Meteorological Society. His book, The Weather of the Pacific Northwest, has become a standard reference since its publication in 2008. And recently, Professor Mass's position as a Seattle icon was bolstered by his listing in the current issue of Seattle Magazine's Nerd Hall of Fame. Described as a proud roster of Seattle geeks with wide renown. So please welcome our Northwest icon, Professor Cliff Mass.
I was really hoping that no one would notice that. I don't know if it's a great honor to be known as a nerd. Is it? I don't know. Okay. Yeah.
Apparently, because they're filming, they can't shut the lights off.
The only problem is that the quality will decline substantially if we can't shut the lights down. At least we can you just shut the lights?
It's either every light or no light. There are two choices.
I would turn it off, but because the trouble is, you know, you won't see that well. It gets kind of washed. Okay. Use the mic. Okay. Let's see. You got to promise not to fall asleep. I teach a 1:30 class, and that's a real problem. All right. Well, I don't know. Why don't we try? You want to try with the lights on or shut it off? Off. Okay, shut it off. Okay, shut it off. Okay, get it off. No, you don't have to see me, as long as you can see the screen. Okay, I don't care if you see me. Okay. Looks like we have a light issue here. Okay. All right. Okay. Let's get going. I was asked to talk about the local implications of global warming, and I'll do that. But then we have the questions. I'll be happy to talk about other things, like the weather of the Northwest, weather forecasting, and even my little pet hobby, math education. So, and I got some things to say about that. Okay, so let's talk a little bit about global warming, and I'm really talking about man-induced global warming and what the implications for the Northwest will be. And I think some things may be a little bit surprising, perhaps. There's a great deal of information about global warming. And not all the information that you get in the media or from other sources is consistent. You probably have noticed that. For instance, just to get close to town for myself, the ex-mayor of the city of Seattle, Greg Nichols, he made a big deal about snowpack in the Cascades. In fact, he wrote a op-ed piece in the Seattle Times noting that the average snowpack in the Cascades has declined 50% since 1950. And it was going to be half again in 30 more years. So, there are some people suggesting that we have already large changes. And if you keep on reading this, he implies this is mainly due to human-induced global warming. Then there's been a variety of environmental groups that have proposed that global warming has caused our weather to become more extreme. You've probably seen a lot of that, all these extreme things happening, all these terrible things happening, and a lot of people are suggesting a lot of the big weather events can be traced somehow to global warming. And in fact, this is from a local this is from an NGO. This is from Environment Washington. When it rains, it pours. So there's one side, and then on the other side, there are others who hold that this global warming issue is really not so serious, and in fact that the lack of warming over the past 10 years indicates that global warming is not a threat. And this is George Will, well-known columnist. I could have given you half a dozen others. The myth of consensus on global climate change. But then there are other questions that many of you have probably asked. And these are fair questions. And a number of the conservative blogs and others have noted this. I mean, how can scientists, meteorologists like myself and others, predict 50 to 100 years from now when we can't get next week's weather right? And I don't know if you've ever verified the 8-day forecast or the 7-day forecast provided by Jeff Renner or one of these other people, and the skill definitely decreases as you get into that second week. But also, there's the other side. I mean, there are thousands of scientists from around the world have come together and have written a series of reports stating that there is an imminent threat of global warming due to mankind's influence. And you've heard about this group, very, very well-known, very prestigious group, the IPCC, which have put out a number of reports. They come out regularly. And each series of reports, which represents the consensus of the overwhelming majority of climate scientists, are talking about the threat being more and more substantial. So the question that I think everybody asks, especially in the lay community, is what is the truth, or what is biased or wrong? What do we know for sure? What are the certainties and uncertainties, and what is going to happen here? And one thing I'm going to make it very clear is that things are going to vary a lot around the world. Now, I think we all know this issue, the basic issue here, and that is that greenhouse gases are increasing. And you know the kind of gases we're talking about, like CO2 is the one that people talk about the most, but it's not the only greenhouse gas. In fact, the number one greenhouse gas is water vapor. But the one that's increasing rapidly because of mankind's intervention, of course, is CO2. And and this is a figure. I think this is from one of the IPCC reports. Oh, sorry. There's 1,600, 2,100, so 2,000. We're around here, and this shows the historical change in the concentrations of CO2 in parts per million. And then there are various scenarios of what's going to happen. Some scenarios have CO2 increasing extraordinarily rapidly. And there are others that suggest that mankind's going to intervene to some degree and reduce the increase in the amount of CO2 in the atmosphere. So there are a number of greenhouse gases, and you know about these. There's carbon dioxide, water vapor, methane, nitrous oxides, and others. And the essential thing that these gases do is they basically act like a blanket. In the same way that a blanket keeps you warm at night, these gases have a very similar influence. And this is something the meteorologists understand very, very well. I mean, this is no mystery. The interesting thing is the greenhouse effect doesn't happen in greenhouses, you know? Some people call it you really should call it the atmosphere effect. So greenhouse effect does not happen in greenhouses, strangely enough. And the idea is this. If you had a planet here with no atmosphere, you know, that you've solar radiation's coming in, right? That's the sun, that's warming. And then what would happen is that the surface heats up, and the surface of the planet would emit radiation. I mean, all of you are emitting radiation in this room, okay? Everybody's emitting. I mean, believe it or not. You're emitting most of your radiation in the infrared, but everybody's emitting radiation. So anyway, the surface would emit radiation and warm up enough until you got a balance. Well, the interesting thing is if you put gases in the atmosphere that are active in the infrared, what happens is some of the radiation, which is mainly infrared that's emitted by the surface, gets absorbed by the gases, and some of it is sent back down to the surface. And so it's sending some heat back down that would have gone to space. And anyway, if you go through the whole logic, that actually results in warming. I mean, it's not unlike how a blanket, why does a blanket keep you warm? Okay, it's basically slowing down the loss of heat, and you end up being warmer. So the physics is really quite basic, and we really understand it. Okay. So interestingly enough, that's not what happens in the greenhouse. A greenhouse, so some people initially thought that the glass would be, or the plastic or the glass initially would stop the infrared radiation. It would act in the same way. It turns out that's not why greenhouses are warm. They're warm because the glass prevents the warm air from convecting out. That's the real reason. And it's not the greenhouse effect in greenhouses, strangely enough. Well, we can predict the future effects of greenhouse gases using climate models. Just as forecasting models, these simulation models are the main way we do forecasting. I mean, what's the technology of forecasting? It's numerical simulation. That's my business. That's what I do. Okay? Well, we can either use these computer models to simulate the next weather the next few days, but we can also simulate the weather 50 to 100 years out. And so these are sophisticated computer simulations based on the physics of the atmosphere. Okay? It's almost identical to the weather prediction models. Almost exactly the same models, except we let the gases increase in time. And I'm sorry that's covered, but we use the most powerful supercomputers to do this. I mean, the fastest computers in the world are used for nuclear simulations and for numerical weather prediction and climate prediction. Okay. Now, our models are pretty good, but as I will readily admit, they got their flaws too. They're not perfect, believe me. Anyway, this is an example of the output of one of these climate models. And in fact, this is for the year 2100. And this is the change in temperature in degrees centigrade. And I want you to, here's the scale down here. So you can see that. That's 10 degrees centigrade. So roughly double that for Fahrenheit, right? That's warm. Anyway, this is using scenario A2 for the change in greenhouse gases. That is a fairly aggressive increase in greenhouse gases. Actually, we're right on track for that right now, unfortunately. And what this thing shows is the classic thing that almost every single one of these climate simulations shows, and that is the Arctic warms up more than any place else. Okay? And that's true for a number of reasons. One of the reasons is the fact you get this feedback between what happens is the Arctic ice melts off. The ice normally reflects a lot of solar radiation. When it melts off, the radiation is absorbed by the water, which causes more warming, which causes more ice to melt, etc. But anyway, the greatest warming tends to be the Arctic. The continents warm up more than the oceans. And interestingly enough, the eastern oceans warm up less than the western oceans. Okay? So this warming is not uniform. In almost all of these climate models, we call them GCMs. That's in the business, that's the terminology we use. General circulation models. You ever hear the term GCM? It's one of these fancy climate models that we can run out 50, 100 years or whatever, as much as we have computer power for. So let's talk a little bit about global warming in the Northwest. So that's the big picture there for the world. Here is a fact that you don't hear too much in the media. Number one, it really appears, if you look at the observations, that there has been relatively little warming here in the Northwest. Little warming. And in fact, this makes a lot of sense. Why would we have relatively less warming here? In fact, to tell you the truth, the warming will probably be slower and lesser here than almost any place around. I mean, and it's going to be delayed. In other words, most places on continents are going to see faster warming than here. And it actually makes sense because our weather is dominated by the Pacific, right? We're right there. Almost all our interesting weather is systems coming off of the ocean, right? We're in the mid-latitude, so the westerlies, so the storm systems come in this way. Our weather's dominated by the Pacific. And so we are downstream of an area that's warming up more slowly than most places. And in fact, this shows you the change in winter surface air temperature from 1979 to 2008. And you can see this is not inconsistent with the global models. And one thing I want you to see, that here in the Eastern Pacific, there's actually been cooling during that period of time. So, Mayor Nichols had a problem. Here is the snowpack on the Cascades at various levels. All sites, the red is the lowest 25% of the sites, the highest are the green. And what I want you to see is that, there's a lot of variability there, but actually there's no real trend. In fact, I did a paper on this that's recently published in the Journal of Climate in which we document this. In fact, we went much further back. And basically, since we went back to 1976 here, there really hasn't been any trend. And if you look at the temperature of the air coming off the Pacific, there hasn't been any trend either. And this is not surprising. Okay. Now, I don't want you to think we're going to get away scot-free with global warming around here. It's just going to be delayed here. And the other interesting thing is those global simulations have one problem. They're very coarse resolution. You can't use really high resolution to run these things for 100 years over the whole globe. But what we have done here is a project that I'm involved in and so the people at the University of Washington. We run our weather forecasting models at very high resolution, high enough resolution to actually get the local weather features right, the effects of mountains and land-water contrast. We've run these models for 100 years, being forced by these climate models. And I'm going to show you what it shows right now. We've done this a number of ways, but I'm going to show you one of these simulations. What I'm showing you here, this shows you here the change in surface air temperature the change between the 1990s and the 2020s for December, January, and February. By the way, you see that says 2-meter temperatures? When you watch TV and they give you the temperature of SeaTac Airport, is that temperature at the ground or someplace else? It's at about 2 meters. That's the official height that the temperatures are reported at. Anyway, here, this is between the 1990s and the 2020s. And look, there's a little bit of red here, but I'll tell you, this is degrees Fahrenheit, 0, 2, 4. It's not so bad. So really, it's not going to be extraordinarily bad. The 2020s are really not going to be that different. Well, now we get the difference between the 1990s and the 2050s. And we're starting to see some of this darker red here, right? Look at that, okay? And there are these bands of red. And it's going to turn out that these are the places where the snowpack is melting back, okay? So this is December, January, February, okay? But then now let's go to the difference between the 1990s, the 2090s. And it's a different story, okay? Really, if you look at the change in temperature with time, it's like an exponential. It starts slowly around here, but by the end of the century, it's getting pretty serious. And these are large values. This is 10 degrees Fahrenheit over here. This is a different world. Just to show you the number of summertime days with the maximum temperature greater than 90 degrees in SeaTac, we pulled off that simulation. 1990s, 2020s, 2050s, 2090s. The number of days per decade. And look at it, 2020s, you're going to hardly need air conditioning, right? You won't need air conditioning. It won't be any different than it is now. 2050s, it's increasing. 2090s, it's really a very, very different world. Now, what's probably scariest is the change in snowpack. This is the change in snowpack between 1990 and 2090. And that is where we see it. In fact, you can see the banded structure right over here. I mean, you see these changes. Look here in British Columbia. We're talking about the loss of maybe 40% of the snowpack over here. Man, that's pretty serious stuff. There's no increases. These are decreases, serious ones. How about going to, people like to go to Stampede Pass, right? It's about 4,000 feet. It's about the same height as a lot of the ski places in the Cascades. And this shows you the change in the amount of water in the snowpack there. The water content for various months. Okay, here it is, down here's the months. For the 1990s, 2020s, 50s, and 90s. And you can see, 1990s up here, 2020s, 50s it's down maybe 25% or 30, but the 2090s is a different world. And it's not a good one. So my recommendation to you is that I would not get that annual pass to Snoqualmie Summit and probably Stevens in the 2050s. So the younger people in the crowd better keep this in mind. So the biggest problem really for us around here is the loss of snowpack. Because snowpack is important for water here. Because it's not, if you look at the simulations, we're not going to have less precipitation. We're going to have plenty of water. It's just we're going to have less snow. And more of it's going to fall as rain, especially in November. And and the snowpack is important because that's our other reservoir. That's the water we use as we get to the middle, late summer and the fall. And it's also important for agriculture in eastern Washington. So it's pretty serious. We could engineer our way out of it if we built more dams, which have, of course, environmental issues. If we built more dams to save water, we could probably get away with it. But we won't have the snowpack. The snowpack will be way down. So, I want to get back to a question that many people have, and especially some of the conservative bloggers. How can we predict climate 50 to 100 years from now when we can't forecast next week's weather, right? I mean, that is a fair question. And there's the answer. This talk is not connected with any political party. Well, the most important thing is there's a few things to keep in mind. Weather prediction and climate prediction are completely different acts, very different things. When you're forecasting the weather, you are forecasting basically the exact state of the atmosphere into the future. You're predicting that the low center will be there, that the temperature is going to be this tomorrow afternoon at this time. That's what weather forecasting is all about, right? Well, when you do climate prediction, we don't do this. There is no way that we can tell you that in 2090 it's going to rain in the afternoon of January 23rd, right? We're not trying to do that, okay? We can't do that. But when we do climate prediction, we are predicting basically averages or statistical quantities. What's happening to the decadal trends of temperature, things that are much broader, averaged over long periods of time. That's what we try to do with climate prediction. So that the mean winter temperatures will be 3 degrees warmer over the Pacific Northwest or something like that. That's what we do with climate prediction. And it is actually much easier to do that. And one reason we can do this is that the average conditions, averaged over a period of time, is really fairly closely controlled by the amount of radiation coming in. That's when we know if we have the greenhouse gases, if they're increasing, if we have a rough idea what the greenhouse gas increases will be doing, we can figure what the radiation effects will be, and that gives us a handle on what the average temperature change will be. So I think we can get some handle on these averages because things are so strongly forced by the radiation balances. So the bottom line, it's reasonable to do this kind of thing. Now, one issue that we've heard a lot about is should we expect stronger storms and more floods here in the Northwest, Here in Port Townsend in Seattle, will we expect global warming to bring much bigger storms? And I keep on seeing the media throw this around like it's an accepted fact. And I think that the correct answer is we do not know. And there's actually, by looking at this logically, there is actually no reason to necessarily expect stronger storms here in the Northwest. Well, first, what's happened over the last 50 years? It turns out the number of windstorms and floods has increased during the last several decades over Washington state. But it's actually decreased in Oregon. If you go to central and southern Oregon, northern California, the number of floods has decreased. The number of big windstorms has decreased there. And in fact, I have a paper that was just accepted in the Journal of Hydrometeorology that we're going to be talking about that. Now, why could things be different than what some of these global warming suggestions indicate here in the Northwest? Well, a lot of the floods and the big windstorms are closely associated with the jet stream. And jet stream is a current of relatively strong winds centered in the upper troposphere, the upper part of the lower layer of the atmosphere. And it turns out that many of the climate models that I told you about before actually indicate that the jet stream is going to move northward under global warming. Well, the question is where that jet stream is going to be. If it moves far enough north, we could actually have less floods. We could have less windstorms. At this point, I just don't think we know. I mean, there's some arguments that the Earth will warm up, there'll be more moisture in the atmosphere, and therefore you'll get more floods. Well, on the average, over the whole globe, there will be more precipitation. But every area, this is local effects, and we're so strongly controlled by this jet stream. If it moves north, things could actually be very different than that. The last thing I want to mention is this whole issue that a lot of the sort of conservative blogs have talked about, and that is the fact that we haven't seen a lot of warming during the last 10 years, okay? Even though the last 10 years have been very warm. These have been some of these have been warm years, but the trend upward has actually ceased for the last 5 or 10 years. Here's a plot over here of global average temperature. This only goes to 2008, but basically we were warming and then it's kind of leveled off a bit. And some people say, well, you don't have to worry about it anymore. But the truth of the matter is that one should expect this kind of behavior, that you could level off for 5 or 10 years, and especially now, and it doesn't really mean anything. The atmospheric trends that we see plotted on maps like that, they are a combination of two things probably, or two main things. One, the upward trend due to man-induced global warming, the greenhouse gases we're putting up there, but there's also natural variations. Even if we weren't doing anything to the atmosphere, there would be natural variations, and which can be quite significant. So basically you have this sort of signal to noise issue. You have one long-term trend going up due to mankind's impacts, but then you have this variability on top of that. And so in the early stages of the warming, where we are right now, it is quite easy for the natural variability to overcome the upward trend due to the greenhouse gases. And that's not surprising, where basically the natural cooling balances out global warming. But eventually, as the global warming due to mankind increases, that is going to overwhelm the natural variability. And all the simulations indicate that that'll be happening by the end of the century. I mean, here's some examples of it. You can see the trends, and you have these level off periods. And it's happened before, it's going to happen again. And we're kind of used to this. And those of you who invest, I mean, it's the same thing. You may have this general upward trend of the stock market, but you got these level periods, right? I don't know if you want to call that natural variability. You can call it what you want. The interesting thing is that, although there'd be losers in our area due to global warming and the loss of snowpack, there may be winners. And that may be the wine industry in eastern Washington. And some of the fine red varietals, especially of the red wines, the Cabernets, which were better down in California, they're going to move up to us. And they're going to be in real trouble in California. So the wine industry, it looks good for. So anyway, so let me end with the bottom line of all this, and then we'll open up to questions. You know, this global warming stuff, it's really serious business. We are fortunate to be living in a place that it's probably going to be delayed and a little bit weaker than the rest, okay? So that's good for us, I guess. But in the end, we're going to see it, and especially by the end of the century. Those are the younger people in the crowd. You're going to live to see this probably. And the main issue will be a loss of snowpack and water supply. And you know, you got to be careful. You can't believe all the hype and false information that is being made available to you from both sides. And I think with that, I will end.